So little background from where I come from. So we are one of the 17 national labs of United States, and Ames National Lab is the smallest lab focusing very special expertise that called material design, both from fundamental and their uses. And we are located at beautiful campus of Iowa State University. Again, this is the only national lab that is within the any university, and that has benefits of it that we get bright students who comes for undergrad and graduate, and we can interact and benefit both ways. Both national lab, they can get exposed to national lab cutting edge science environment, and we get really smart kids to work with. So I will be talking about based on the audience at very high level, just to introduce several things that can be useful. And if you have any technical question, please don't hesitate to ask, because I'm not trying to make it too technical that you are not able to follow. So I will be giving a little background of magnetic materials and why they are useful and how they are connected to sustainable future and how we design at Ames Lab. And then some takeaways for everyone, that what we can take from this talk, and then where in the future we stand based on the current scenario. And all the works are based on these three works you can see on the right-hand side corner. You guys can follow and see what I'm talking about. So, okay, so basically, I will start with just an overview that what sustainability means. Currently, in our perspective, we are using mostly the fossil fuels. And fossil fuels means you are putting a lot of carbon footprints that is going to or leading to the really bad environmental impact like global warming, right? And so what is the goal as a scientist, a person, if you think what you can do, can we reuse that what we are living in the environment? That's why there is a huge effort in the carbon capture, that can you capture the carbon dioxide or the carbon components that you are leaving into the environment? How you can do it? Easiest way is to recycle, reuse, and the third one is reduce. How you can reduce the uses. And reduce only can happen when you have some kind of new discoveries, new changes in the way you use things. That will lead to sustainability. That you do not use things like already like going away from us, like for example, fossil fuel. If you can reduce the use, you can really be sustainable because you are making your environment cleaner. And that is a better and greener earth. That's what sustainability in general people think about. What sustainability means for us material scientists or engineer who are working in this field trying to address this sustainability issue. Materials are the fundamental or foundations for anything you want to do in addressing this sustainability issue. If you don't want to use fossil fuels, what is the alternate? You have to design new solar cell. You have to come with the new technology that can replace the vehicles currently used, or you can want to use refrigerators or air conditioners that do not use this like expensive heating, cooling that is leaving more carbon footprints in the environment. So everything is going back to the materials. So that's why I put really lot of emphasis that understanding material, designing is a good or great help in keeping the sustainability addressed in coming 20, 30 years. So if you see, I have put some stars. These, since I'm talking about magnetic materials, I will be discussing and pointing out criticality of and supply chain issue of these magnetic materials in current scenario. So if you see, there are 5 main components that normally industrially people use to make magnets. And in a moment, we will see why these magnets are important, why we are focusing on these magnets only, not all. See, each element are important, but there are certain element class that are more prioritized in terms of supply chain and uses than others. And magnets are one class, such class. So just going back to the very basic, what we understand are in my high school or undergrad, and any situation when you talk about the magnets, it's very simple, right? Any object that is capable of producing magnetic field is a magnet. And in general, from our childhood to today, when we are doing or talking to anyone, we talk about iron-based magnets. That's simpler to know and it's simpler to connect, and people understand very easily. But this is not the one magnet that is used industrially or in your day-to-day life. Either you take refrigerator, either you take electric cars, or you take windmill power generation. Everyone uses very sophisticated kind of magnets, the one I highlighted as a critical in previous slide. So that's why like magnets are critical, because there are so many things you can do for a sustainable and cleaner environment. And that's why they are preferred over any kind of other material class in periodic table. And where in the, just to give an example, you cannot do much with the wind power generation if you don't have a right kind of magnet. And any magnet you use, they are coming from rare earth based lanthanides. They are very expensive to first to make. Secondly, supply chain. All the supply chain is in the Asian countries. So bringing them back, if somebody says, I will not give you any rare earths, how to find the substitute? Can you design some materials that has no such issues of supply or bringing back from some other place? So, okay, so now again, I think I put some point before how the magnets are connected to sustainable future, and there are many things. And first thing, anyone, if we talk about this car, we think about Tesla, right? It's really a remarkable change in the automobile industry they are bringing to the for cleaner environment. So, but again, you need magnets, because if you want to replace fossil fuels, you need to store energy. And to drive them, you really need magnets. And those magnets are made of rare earth materials. They are critical, very critical to get, to process, to even make them in a shape that is necessary to use, or you can, any way you can use it. Next are, I will say the next one is like, suppose you want to use electric bicycles, that is other application. Then comes to day-to-day life, like your phone, your computers, your storage devices. Everybody need magnets, are better and better. So you need to make them better, because you need more. Suppose you take your phone, you want to store more pictures, you want to store so many more things on that. Even if you do on the cloud, people who are creating those storage, they need such materials to create that backhand space for you to store those things. So there are so many real life applications that magnets can supply. And the second, or we say the other revolution in next 20, 30 years, where the Ames lab is the leader, is the rare earth materials in magnetic refrigeration, like in your cooling and heating system. That is going to change the market completely. And the magnets are the main driving force. And given the supply chain issue of the rare earth magnets, we need to discover something new which have similar properties, but they are cheaper to produce or easily available. So there are various applications. So I don't want to spend too much time. Just I'm trying to highlight how and where the magnets are important and how they are connected to your sustainable future. Because if you do not replace or use them, you are going to depend on the fossil fuels, which are dying out, like in maybe 100 years. Next two generation might not be able to use the fossil fuel, or they're not available in the market to use. So there should be a sustainable change in the market or in the research, in the industry and academia both. So if you see the forecast, just simple what our daily life uses a car, they're going to be a twofold change or more change in demand in all over world. And for that, you are going to have that scaled up in material amount of material you want to produce. But the rare earth, again, those magnets currently available are very limited. It takes huge amount of time to process and produce them. So you need alternate cheap source that can address this challenge for coming future. And again, I'm talking about the magnets. So rare earth are really the way to go to how currently, at least in current research and academic scenario or industry scenario, they are the one which you need to replace or provide for the car industry. So you are going to see almost 700% jump if you want to address the need of the 2030 car market or any such market which needs these materials. So what you need? So you need permanent magnets, not necessarily rare earth magnets, right? So what your goal? Reduce the critical materials, reduce criticality. And that's how you are going to achieve the zero carbon energy solution by 2050, at least from the US point of view. We are trying to reach to the level where we should have zero carbon footprint by designing new materials, by designing new devices that uses less energy, like there's less emission in terms of carbon, anything. So everything counts. Okay, you want to design new materials, but if you see a periodic table, and I'm just talking about if you see an arrow in the bottom, it's rare earth lanthanides. So even if you just take a 5-component system, there are millions of combinations. You cannot just sit down and just say, oh, I will choose this element. People already were smart enough, or our ancestors were, our people, our previous generation were smart enough. They already tried everything possible. So you have to be more smart, or we have to be smarter to develop approaches, right methods, right kind of algorithms that can provide you a guideline that can help you to pick intelligently, not just randomly or Edisonian way of trial and error. So you can see you have a path forward, but you need to be very diligent and wise in choosing your approach, how you do it. So how you will address this challenge? This is a further one more challenge from the design when you're starting to think about it. Okay, you can find an alternate material. That's what we discussed, right? We can replace existing materials which are expensive, scarce, not easily available, has supply chain risk. We can come up with new material class, but how? You need a method which is faster. So machine learning, okay, now I want to introduce machine learning, because machine learning is a statistical way of looking at huge amount of data, millions of data points you have, how you want to find a trend. They are very fast, but everything depends, and the data class, depending on system or application you choose, it is not very well defined or well done, like not well organized. So there is so much possibility of error, that even if you try to use that information, you are going to make so many mistakes. It is faster, but it's very difficult to find out the right trend based on the existing data set. Then robustness. So how you can make things robust? Density functional theory, I think our previous presenter talked about DFT. That is very robust. It's based on quantum mechanics, uses physics. It follows all the laws of physics, but certain approximations. It is robust, but it is so slow that if you use it, it will take 3 generations to reach to this combination that you can do with machine learning. So what is the intelligent way to find alternate materials? How to fuse these two? Use quantum mechanics or laws of physics to combine them together to address this challenge. I think that's the only way I see forward. And I think more people who are working in this area, they understand this need. That's why they call it physics-based machine learning, right? You have certain components of physics that are critical to address or include material information that is not possible for machine learning to do. Because machine learning just does what? It takes your data, it does what you want. So whenever I talk about machine learning, I put a point or a comment that those things are machine learning is as smart as the user. If you are not smart enough, then you will get what you are giving. And that's why combining and learning the basics when you are starting is more important than just going to do it. You will get something like garbage in, garbage out. Can you really design or guide the industry with that? Can this be impactful? Can you make an impact to address the sustainability or green energy effort of all the countries, including all, like I will say, the north side of the globe where we are here? So, okay, so here's a flow chart. Okay, what you can do, how you can use machine learning. You can assess for property prediction. Suppose for me, using machine learning, I want to design a new magnetic material. So critical temperature or like transition temperature of those materials are very, very important. If you can enhance the transition temperature of those materials, you can use them for longer time. longer temperature range without breaking or destroying the material. So that is the one way you can address this challenge. So other one is like, okay, that is my target property. For example, to provide a proof of concept that it works, physics-based machine learning works. Second is then use that information fused with DFT to design a new material class. So I understand now material, that for existing material set, what are the key foundational or fundamental features that drives these properties. Now I go to DFT or quantum mechanics and say, okay, let's extract that all information for all relevant material class and put back into the machine learning and develop your model that has now physics informed information into it, and that will follow all the rules, regulations of quantum mechanics, but still you are doing much faster because using machine learning statistical approach. So that is the framework people right now working on to design such kind of framework, which has both the component. You don't have to spend too much time with DFT, but you also have certain components so that you have very well-defined path or data set that is critical to design the model. So just provide a proof of concept to you all that, okay, so we developed the database which was unavailable, not present for, at least for rare earth magnets are completely scarce. Each DFT based method or theory or software has very different performance for. So somebody has to be knowing the physics of rare earths before you start doing calculation and understand what you want from those calculation, and then develop a data set and features that are critical to train your model. So based on that, certain features we extracted from DFT, we trained a model and we use random forest based method. Like one of the like linear regression scheme that you can use that is quick. If your data is good, you will get really good results. So if you see in the left-hand side, we saw the literature experimental Curie temperature or magnetic transition temperatures versus predicted data. It was pretty good, I will say. So it was our fourth attempt with the improving the data sets for 1 year, 1.5 years, when we reached to the level where we can get the error of less than 5% in predicting the Curie temperature of any magnetic material, which are like rare earths, which are even really harder. And if you see the error analysis on the right, you can see the distribution is mostly around 0. So error component is also very minimal for this model because we were able to include that physics information that is critical to train my machine learning model. So we choose two compositions, which are like, if you see, I highlighted as a green dots, and we are going to test them from experimentally now. So this is the information you can get in the paper. So I just put it that to know how the model was trained and what are the components were used. And again, just to show you what I mean by physics-based machine learning and what is the physics information, you want to calculate certain features which drive this transition temperature in this magnetic materials. One thing is, if you know about the atoms, atoms has orbitals. And for rare earths or magnetic materials, D and F orbitals are the one which drive or controls all the properties. So what we did, we feed back to the machine learning model the average bandwidth of those uh, orbitals that are involved directly in chemical interactions or chemical, I will say, hybridization that connects with the Curie temperature. And we found that actually the order, when you have the Curie temperature of any material from experiment and you get a bandwidth F and D for that specific alloy, you can rank order them based on the Curie temperature and the bandwidth. That was a remarkable finding that we were able to like fuse into the machine learning model. And that was the reason why we were able to really very accurately do these rare earth magnets. So now this first thing, this is experimental, so I'm not expert from experimental side, but this shows the X-ray diffraction pattern of those two material class we showed. And if you see, they are single phase materials. So both of them predicted alloys, they have single phase. Okay, I think this is some, I'll just. Okay. I will just remove this so that you guys can see this part. So here you go. So this is the TC measurement of those two compositions. And if you see, the predicted Q temperature was very close to, like, TC 632 versus 240 was predicted from machine learning. And they are very close to the same temperature range. Less than 10% error in predicting the Q temperature of these materials using the machine learning model, what has the physics-based information into it. So at proof of concept level, that if, so I will also add a caveat that it is very difficult to extract those information and infuse in the models. So it needs a lot of time as well, even though it makes things more robust in machine learning point of view. So we need to, moving forward, we need to make it more simplistic, maybe use the compositionally averaged, like some simpler models or mathematical tricks to infuse this information so that we don't have to do directly DFT calculations. So there are ways to make it more faster, but when you want to test a hypothesis that it works or not, these are the better way, that you directly go to the quantum mechanical based approaches and try to see how what the outcome you are getting. So the second thing, okay, just to give a slight background, the Jeans factor is the one empirical way of assessing Curie or transition temperature in any magnetic materials, especially rare earth based, was used consistently for a long time. And our machine learning model was, if you see, predictions are showing the linear correlation with the Jeans factor calculated from the empirical model. So it means the machine learning model, after trained with those physics information, was able to capture those empirical physics rules that are used in this class of materials. However, there's one more breakthrough, I will say, in terms of finding, that we found a range of compositions, what you can choose for rare earth in the system. So machine learning models shows really very good predictions, but Dejean's rules break down below the 25% rare earth composition if you go below that. So machine learning physics informed machine learning, I will again emphasize, physics is very important to infuse in any discovery or design you want to do in order to consistently reproduce or develop a reproducible model that can help you design or help other people who want to use it. So I will just give a few conclusions that, okay, if you have, I don't want to read this one, but I will say, if you want to design a material class, you have to very slightly out of the box thinking, that don't just take a model existing and just run it and try to see if you are able to predict something or not. But your overall goal should be learning what new information can you learn that can be useful for next, like maybe other people who don't know about it. If you are spending time, put time to learn something which is non-existent, which is not present in the literature. Just doing it maybe give you a paper or give you some results, but that can you really drive the experimentalist? That, okay, they don't have to come to you, say, can you do this composition? You tell them, can you do this composition? I think this is going to be a really good compared to all other existing material classes. Again, future challenges are really many. It was very basic machine learning model to understand those fundamentals. But in general, what industry care about are much complex quantities. And the database for those quantities are almost non-existent. So there is from our side, we are trying to generate these class of data sets, given the Ames lab is really, I will say, where the rare earth originated and design of rare earth materials. So we are trying to use our expertise in generating these data to improve the existing machine learning models so that we can really predict the properties that experimentalists or industry care about. And they are like microstructure, how your saturation magnetization or coercivity and all the Q temperature we already did. But now when you change a material composition and go into the laboratory framework, actually all three changes simultaneously. You cannot just pick Q temperature and say, okay, go and make it. there are so many underlying physics or properties that change or keep dynamically changing that you cannot control them. So there is, I will say, a trade-off. Understanding each property individually make it simplistic, but for real design, you need to have a fused model which can simultaneously learn simultaneously all three features and predict a new property of interest. Can we do it? Yes, I think we can do it, but yes, we need more effort, more data, more understanding. That's still missing. Thank you.
Thank you so much, Doctor. And we have a time to make any questions. Can you hear me?
Yes.
Abriremos el espacio de preguntas. ¿Alguien tiene alguna pregunta? Podemos traducirlo también si alguien quiere hacer en español. Se la dejamos llegar al doctor.
My question. Okay. My question is, how many years do you think it's going to take to make a real change in magnets?
So, okay, good question. So last discovery which was a real magnet that is still used in industry is neodymium-based magnets, which we've done like 30, 40 years back. So you can see there is no replacement yet for them. So nobody could replace them yet that can have a similar efficiency, similar properties, and they are performing at the same level. So people are trying at their level best. And Department of Energy, where I'm located at, so we have a institution named Critical Material Institute. So we have, like, Department of Energy is investing $150 million just to put focus on magnet design. So to come up with a substitute solution that can replace or have a cheaper materials inside those magnets that have a similar property as the currently used ones. So yes, I expect, based on the work we already have done in Ames Lab, I will say we are testing at the lab scale level or bench scale, and I hope there should be some breakthrough soon.
All right. Thank you.
I could not hear. I'm sorry.
Okay. Do you hear me?
Yeah. Thanks.
Okay.
Yeah.
Oh, okay. I was saying that I was curious about how you trained your model. No, you say that you feed your model with density functional calculations and so on. No, but in these machine learning systems, no, as far as I have heard, no, because I'm not an expert in that, you need a lot of data, no, in order to feed the system and for this system to be predictable, no. So
Yes.
how big was your data collection for your system?
Yeah, that's a good point. Actually, that's what in the beginning I mentioned, that data points in this field is very critical and almost scarce. So for my case, I used 220 data points, but one good point was that all of them were from experiments. And these 220 were selected from almost 8,000 Curie temperature points that exist in literature. So we started with from roughly 8,000 or something, and then we went back to 220. And then on that, we developed a feature set or feature designing or feature engineering to train our model.
Dr. Prashant, thank you very much for your time, and sorry for the mess in the schedule. I know you have a meeting in some minutes, so Thank you very much again for your presence here.
Thank you. Thank you. And thanks for inviting, and hope to see you soon sometime.
Sure, absolutely. Thank you. See you soon.
¿Nos escucha? Hola.
Sí, ¿qué tal?
Ok, en un minuto lo presento y ya puede continuar, ¿sí?
Ujú.
Gracias.
La siguiente conferencia está a cargo del doctor Johan Estrada López, de la Universidad Autónoma de Yucatán, en México. Su ponencia lleva por título Wearable Devices, Present, Future, and Interesting Applications. ¿Podemos poner atención, por favor? Gracias. El doctor Johan Estrada recibió el grado de doctor en Ingeniería Eléctrica de la Universidad de Texas, en Estados Unidos, en el 2019. De 2012 a 2013 trabajó como ingeniero de diseño del año en Vidatronic. En 2017 fue becario de diseño en Power Delivery Group Intel Corporation en Estados Unidos. En el año 2019 trabajó como investigador postdoctoral en el Analog Mixed Signal Center en Texas. Para el 2022 fue profesor asociado en Westwood College, Santa Bárbara, California, Estados Unidos. Actualmente es profesor de Ingeniería Informática en la Universidad Autónoma de Yucatán, Mérida, en México. Sus intereses de investigación actuales incluyen el diseño de circuitos integrados para la recolección de energía y la gestión de energía en aplicaciones móviles y portátiles, así como también el diseño de sistemas embebidos para WSN y las aplicaciones de Internet de las cosas. Damos la palabra al doctor Johan. Muchas gracias por estar con nosotros.
Well, yeah, thank you very much. So I have first two questions. First, if you can see my screen. Yes, hello, can you hear me? Hello. Can you hear me there?
Can you hear us?
I can hear you now, yes.
Sí. Thank you.
Okay, so can you see my slide?
Yes, that's right.
Okay, so I will start my presentation and I will present in English. I have the understanding that probably there's some people there that are native speaking English people, so having some consideration for those people, I will present in English. So thanks a lot for the invitation, and I will gladly present you this subject of wearable devices, present, future, and some interesting applications in this area. You will feel that in this presentation we'll be moving forward towards a more applications area rather than like pure physical research. But nonetheless, I hope it will be very interesting to you. So the content of this presentation is the following. We are first going to describe what is wearable technology, and then we are going to show what are some current and real-life applications in the market today. And also then we are going to speak about what are some of the most interesting applications in research. And we are going to discover that in the research area, there are more ambitions towards what can be done with wearables. And then I'm going to show some applications and solutions of my own research group in the design of wearables. And then we are going to conclude this presentation. Okay, so what is wearable technology? So wearable technology, which can also be named wearables for short, is a term that is generally used to refer to smart devices that are designed to be worn on the body. So with this very general definition, we can group in this area of wearable devices, many different shapes, forms, applications, types of devices. So we can find in the wearables area what it's now known as smart fabrics or smart textiles. So we can have like a smart shirt or smart gloves. There's also some patchable devices like some kind of electronic tattoos or electronic skin. There are, of course, a series of wearable accessories, and the most well-known are the accessories that are worn on the wrist, like smartwatches and fitness trackers. But there are also some type of accessories that are different and can be worn in other parts of the body. And also there are implantable devices that are mostly used in health applications and medicine applications. And well, this is also a very interesting area of research. Okay, so why speak about wearables, or why be interested in wearables? Well, wearables, it's an area in the technology market that is growing a lot. So this graphic shows the trend of how the market size in the United States is expected to expand in the following years. And we can see that already the market of wearables is representing more than $10 billion in expenditure. And of course, this is a very important market out there. So there's a lot of interest in the consumer side of products. But there's also a lot of interest in wearables in the area of academia. We are going to show that in a little while. So wearables have also become an increasingly popular research topic in the recent years. So this graph that is kind of outdated because it shows up to 2015, but it still demonstrates that any keywords in papers that have or include wearable is like exponentially increasing, and the number of papers that include this keyword, and it's even going beyond what was initially contemplated in the wireless body area networks. It's kind of a similar area of research, but not quite the same. And it's has grown even more than the WAN research papers. So as you can see, there's a lot of interest, there's a lot of money, there's a big market, and there are many possibilities out there for companies, startups, and researchers. So I'm going to show you now some interesting example of actual commercial wearable devices that are there. So the interesting thing about wearables is that some of these devices that I'm going to show are going to be there in the market a couple of years, and probably they are just not going to get a real stronghold in the market, and they're going to disappear. There are a lot of devices out there that have appeared and then disappeared. Many ideas are coming and going, and so not of all the devices that get to the market are a direct hit, and some of them are just going to disappear. But nevertheless, there are real examples that you can actually buy right now. So for example, this continuous glucose monitor device, as you can see, this lady has this patch on her arm, and this is actually measuring the level of glucose in the blood without having to do the piercing on a finger. And this is a device that it's connected through Bluetooth to your cell phone, so you can see on your cell phone and continuously monitor your level of glucose with no without the inconvenience of having to pierce your fingers several times over the day. This other device in the middle is a safety and wellness device offered especially to the market of people of age. So this device is marketed to be used to track the activity of the person, so their families and relatives can monitor if they are being active. And it also have a fall detection, so accidents can be detected. And also the level of activity is measured and transmitted wirelessly over the web to the relatives, so they can have a confidence of having a more direct supervision of their old relative. And finally, we have this very interesting device, is a tracking ring. So you use this ring during the day, and you can track your body temperature, your oxygen, your heart rate. You can monitor your sleep patterns, and whatever is already common on some fitness tracking and smartwatches. But they are offering these features in a more compact presentation that is a ring. And of course, most of these devices are several $100s worth in costs. So they are not really accessible to many people in the consumer group. There is also a lot of interest of wearables in sports. Probably you are aware of the middle one. It's been presented and showcased in many sports sections of news programs or sport focused programs. It's a wearable device that can track how fast, how many sprints, how many miles, the temperature, and basically give an overall performance of a soccer player or any type of sports that is on a field like basketball. So it's been used, and it's actually used in a lot of professional teams to be able to have a record of the performance of their players. The two other products on the streams are not that well known. Actually, this swimming activity tracker, I think, is still in a crowdfunding period. So they are starting to sell it, but it's not quite a success in the market. It's a device that is supposedly to be worn during your swimming session, so you can track your performance, number of strokes, speed, and another type of performance tracking. And the one on the right, it's like a smart sock for running, and this is coupled with artificial intelligence application. So you can see while you are running how fast you are running, your pace, if you are actually it's an important thing is that you're actually having a correct stepping while running or while walking, so you are not going to get injured in your knees. So it's a very interesting application. It seems like, I don't know if it will be actually comfortable to wear this, but it's an actual device that is being sold in market. So these are just some examples. There are some more that you can probably find out with a search in the web. And now we are going to show some applications that are being showcased in research papers. So as you can see, in research, people venture to do more interesting things. They are not risking, their investment money. So there are many other ideas. And as you can see, wearable devices are being proposed to be designed to be worn in many places in the body, in the head, in the chest, in the wrist, in the arm, in the feet, or in the legs. Probably I would like to show or speak more, focus on 3 of these devices. So the ones that we have here, it's like a belt that is used to monitor your posture while you are sitting. And when it detects that you have a bad posture when you are sitting, it's going to tell you via an audible signal, or you can also send a signal to your mobile device, like your cell phone. This other one at the right, that it's like kind of like an electronic patch that can be adhered to the arm, is proposed to be able to detect tremors in the arm. This is a very interesting application because one of the most important issues when we speak about neurological disorders like Parkinson, Alzheimer, or other disorders that generate involuntary movement in the extremities that are called tremors, can be detected very early in how you walk, like in the cadence and how you move your arms and your legs when you are walking. And this can be detected, actually right now, professionals in medicine do it with lab experiments. But if you want to have real life continuous tracking and monitoring, it can be done with this type of devices. And the one that is on the bottom right is a similar device proposed to also detect at the early stages of Parkinson and Alzheimer, but with a device that is worn on the leg. So on research, there's also a lot of interest in novel ideas and applications, especially in medicine and in sports, as I'm going to show now. But what are the main challenges? Okay, there are many challenges in the design of wearables. There's a lot of concern about the security and privacy of data, and also of making devices that are standard. If you have smart devices in your home, you will experience that none of them are actually compatible with each other, and it can generate some frustration in the user. But probably some of the most important issues are reducing the cost of the devices. I mentioned that some of the actual commercial wearables out there cost hundreds of dollars. So reducing the cost of the devices is important to be able to reach to a wider market. Also, the area of applications, like designing new applications, and also having an extended lifetime. Another issue with wearables is that you have to keep charging and recharging your batteries. And if you are trying to propose a wearable that is used to continuously monitor either your performance in sports or your health, you don't want, to take the wearable and not been using it a couple of hours while it's being charged. So how can we solve some of these problems? Well, the solution is in using smart algorithms like artificial intelligence and what is also called energy harvesting techniques. And I'm going to show some of these ideas in the following slides. So here I'm showing a device that we are proposing to be used for an application in sports, but for to be more specific or focused in extreme sports like surfing or skating. And most importantly, the idea is not only to be able to measure performance, because this is basically very easy to do in a way of speaking, but actually to be able to predict performance or measure the quality of the motion. In surfing, if you are familiar with this sport, you will be able to know that this is a sport that is judged, in a kind of subjective way by the judges. But if we can have a device that is actually able to measure the motion of this surfer and compare it with what will be a standard, a golden standard of this is like the perfect motion, and then a more objective way of judging the sport and the performance of the players be done. So this is a wearable prototype that has been done, and we have been testing this device in the lab with different maneuvers and a 3D motion capture lab. I'm going to describe this lab in a more extensive way in a moment, and also in the field with skaters, right? And this has been a conference paper that we published recently, the last year, and we have already data coming from our experiments, and now we are going to focus on using this data and feed it into machine learning algorithms in order to be able to compare these maneuvers and the performance of our test subject and compare it with a database. And this is the problem related with the question that was asked in the previous session, that there are not many data sets and there are not many information that is there. So generating our own data sets, it's also a process that we are following right now. Well, speaking about energy harvesting, we have been interested in harvesting energy from body motion. If wearables are devices that are worn on the body, why don't you use the energy that is generated by the motion of the human body to feed power to our devices? So we have been also interested in investigating how we can best harvest energy from the body. So what we did in this work is to go to a 3D motion capture lab. So it's a lab that can detect the motion of a reflective sensor, and this reflective sensor can be attached to different parts of the human body: chest, arms, wrists, legs, the feet, the knee, and we can actually detect and have a live motion tracking. And we did experiments in this 3D motion capture lab with people running and walking in a treadmill. This is the methodology that we follow. We test with 4 subjects of different ages, different heights, both from male and female. And we tested with different speed ranges, walking and running. So this is the type of data we capture: the actual position of and velocity. We're going to show also the velocity of the reflective marker. And also, if we have velocity and position, we can actually obtain acceleration. And if we do the FFT of the motion, because you can see this is a very periodic motion, we can have the amplitude and the frequency of the motion pattern. This is just an example of one of the experiments that we did. So at the left, the red plots are actually showing the position of the marker at different parts of the human body. Chest, you can see in the chest, there's practically no discernible pattern, but the ankle, elbow, knee, and wrist show a very reproducible cadence of motion, almost sinusoidal. And the speed have been measured, and as you can see, we can also obtain the acceleration. Here we have the presentation of the motion. It's very also interesting to discover that the motion on this part of the human body follows a very close pattern that can also be predicted and can be taken advantage of to design an energy harvest. We can predict the power that can be harvested with this type of motion. And going a little bit faster, this is a specific electromagnetic energy harvester device that we designed to harvest energy from the body motion of the knee. We try to design this harvester to follow the pattern that we can discover at the knee, and it's being fabricated in a 3D printer, and we have a magnet. And as we can see here, if this magnet moves through a coil, we will going to be able to generate a voltage and then harvest energy from the body motion, let's say, for free. So we created or fabricated different prototypes with different dimensions, and we tested them. And this is a plot of the voltage that was measured in some of for the different curvatures that we fabricated the devices. And we were actually able to harvest not that much power, in the order of hundreds or of microwatts. This is very promising still, considering that this was a work done by an undergrad student. I think that the results are pretty promising, and if we extend this work for a graduate level, most probably we're going to be able to refine our design and get better results. This is another application that we developed. So moving a little bit faster, it's just the idea that we can also use intelligent algorithms, smart machine learning applications to extend the battery life. What about if we smartly transmit wirelessly our data? So now every now and then, if you use a smart device, you will have a device that transmit data wirelessly and on a specific uniform rate of time. But what happens if sometimes the data, it is not of interest to be transmitted? So we can actually be able to predict if the data that is being measured is worthwhile being transmitted or not. And also taking into consideration the energy that is stored in the battery or the supercapacitor. So this is a device, a prototype that we designed to be worn in the wrist. And it's a device that measures the level of oxygen in the blood, temperature, and heart rate. And it's being powered by a photovoltaic cell. And well, the idea here, just to summarize, is that we applied a machine learning algorithm, a decision tree, to be able to, considering a multimodal data set, the oxygen level in the blood, the temperature of the human body, the heart rate, and the voltage in the capacitor, we were able to adjust the transmission duty cycle. So comparing with a uniform sleep period, we were able to smartly decide if we can transmit more frequently or reduce the data rate of wireless transmission. And in this way, we were able to prove that we can extend the battery life like 3.8 times compared with just a uniform sleep period or data transmission. So just to give a summary of this talk, wearable devices are a technological driving force in the market, having economic impact of billions of dollars nowadays, and is expected to keep growing. And there is a wide and exciting range of many applications coming in the future, as you were able to see, in medicine, in sports, but also in industrial applications, in the environment and smart home. A very crucial challenge is the extension of battery lifetime. Energy harvesting can be used to extend the battery life. We also demonstrated that it can be done from the body motion, and that smart algorithms can be used to make possible the conservation of energy from the battery or the storage device. And also, one more conclusion will be that this is a very interdisciplinary research area. It requires physics, mechanics, electronics, computer science, and many other areas like bioelectronics and medicine. So, well, many thanks for listening. I'm I'm available for questions if you have any. Thank you very much.
Thank you, doctor, for your participation and for being part of the event. And we are going to open the session of questions. ¿Alguien tiene alguna pregunta? Oh, okay.
Vamos a empezar por aquí enfrente, ¿sí?
Which do you think is one of the most important wearable energies? Wearable applications for the people?
Well, yeah, I will say that the most important area of application nowadays will be health and wellness. To be able to predict in early stages of development some diseases, this is key for the treatment of the person or the patient. And also, once that some disease or disorder has developed, to have a continuous tracking of how the illness is developing, it's very important. And also, COVID-19 pandemic show us that being able to monitor the health of a person without being close to him or her is also very important. So I would say health, medicine, and wellness is the most important area. Wearables.
Thank you.
Yeah.
Tenemos espacio solamente para 2 preguntas más porque sigue otra conferencia. El doctor Murat.
Yes.
Okay. As I understand, so you're trying to make your own devices, right?
Yeah, I mean, I will say that devices or prototypes that we have fabricated are within the state of the art of what a smartwatch are. We are more focused on the application side of.
Yeah, I see. So just I want to understand what is the difference that you can report in your wearable devices comparable to the other ones, like to the most famous Apple or Samsung or some other ones.
Yeah, okay. So I will say that right now, the application side of this type of devices, like smartwatches or fitness trackers, are very conventional. They are just going to measure, let's say, your temperature or your oxygen level and give you the number. And that's it. And I will say the most exciting thing right now of an Apple Watch is being able to detect that you've fallen and call 911.
Exactly, yeah.
Yeah. So they are still very conservative in what applications are done. As I was showing and discussing, there are many very interesting applications that just appear in the market and then 1 or 2 years they disappear. There are very novel ideas, but probably the level of development in the application is not mature enough to be in the market.
Okay, thank you so much.
Yeah.
Okay, just one last questions. Is there an app right now that you guys might be using, or that you are using right now, or you are piloting using artificial intelligence, or someone that you can advise us, so we can use them for free in our smartphones?
Okay, so let's see if I understood the question. So yeah, we are using right now machine learning or artificial intelligence in our research. As I show, one application is being able to intelligently use the information that we are receiving to efficiently transmit the data, so we don't deplete the battery that fast. And there are many, let's say, application programs in AI that are freely available, like TensorFlow. It can be used also in MATLAB. There are many algorithms out there in Python. So yeah, if you're asking if you can get hold to machine learning proven algorithms for free, yeah, it is possible. Yeah, it's kind of a really mature area right now.
Por cuestiones de tiempo, ya no podemos hacer otras preguntas. Vamos a le damos un aplauso al doctor profe que lo introduce.
Thank you.
Seguimos con la siguiente ponencia, que lleva por nombre Local Atomic Structure of Heavy Nuclide Provide de Transmission Networks, impartida por el doctor Francisco Javier Espinosa Paler, que le agradecemos que esté aquí presente, y lo voy a presentar. El doctor Espinosa es actualmente director de investigación de la Universidad Magistral de México, de Mérida. Obtuvo el título de ingeniero en sistemas computacionales por el Instituto Tecnológico de Mérida y la maestría y doctorado en ciencias con especialidad en física aplicada por el CICATA del Instituto Politécnico Nacional. Fue asistente de investigación del programa clínico al laboratorio de radiación sincrotrón en la Universidad de Stanford. Investigador postdoctoral asociado en el Laboratorio Nacional del Noreste del Pacífico en el grupo de biogeoquímica ambiental. Investigador postdoctoral asociado en la División de Ciencia y Tecnología de Materiales MST 8 en el Laboratorio Nacional de los Álamos en Estados Unidos, recibiendo ahí el premio al desempeño distinguido. Actualmente dirige un laboratorio de crecimiento y caracterización de nuevos materiales en forma de película fina. Su investigación se centra en el descubrimiento de distorsiones e inestabilidades atómicas locales en la red cristalina de materiales complejos, utilizando principalmente espectroscopía de absorción de rayos X por luz de sincrotrón. En los últimos años ha dedicado parte de sus esfuerzos al estudio de la relación estructura-propiedades de semiconductores formados por elementos abundantes y no tóxicos, así como el estudio de semiconductores altamente impurificados con posibles aplicaciones en células solares de tercera generación y materiales fotocatalíticos sensibles al espectro solar. Actualmente estudia la relación de estructura-propiedades de los compuestos semiconductor grafeno. Les doy la palabra al doctor. Muchas gracias por estar aquí con nosotros.
Gracias. Gracias por la presentación y a todos ustedes por estar acá. ¿Sí me escuchan bien? Perfecto. Entonces vamos a hablar, ¿verdad?, de la estructura atómica local de materiales, ¿no? Y con... Perfecto. Entonces vamos a hablar de la estructura atómica local del sulfuro de zinc altamente impurificado con algunos metales de transición. Entonces, ¿cuál es la motivación? Estaba yo pensando, ¿no? Ahorita mismo sentado aquí escuchando las otras pláticas, ¿y cuál es la motivación? ¿Por qué queremos estudiar materiales? ¿Por qué hacemos cálculos? ¿Por qué hacemos? ¿Cuál es el objetivo de la vida? Es algo que tienen que plantear. Es una vida prolongada, saludable, creativa. Entonces, para tener todo eso, se estudian estos materiales, para tener los procesos limpios, los procesos que necesita el mundo para sostenernos y para tener una vida plena. Entonces, bueno, la motivación aquí, lo que podemos nosotros aportar realmente es un granito para poder avanzar el estado del conocimiento. Entonces, el sulfuro de zinc es un material pues abundante, no tóxico, tiene un ancho de banda bastante amplio, ¿verdad? Y tiene algunas aplicaciones de las cuales no vamos a hablar, pero en sensores de gases, detectores de UV, catalizadores, celdas solares, ¿verdad? Y puede tener otras muchas aplicaciones, así como otros muchos materiales las tienen, ¿no? Podemos hacer una ingeniería del ancho de banda, ¿verdad? Haciendo distintas aleaciones con él. Por ejemplo, aquí se está estudiando el sulfuro de zinc, el sulfoselenuro de zinc, entonces puedes ir cambiando el ancho de banda, para ir cambiando las propiedades. Puede ser un material que sirva como electroluminiscente, para láseres, para spintrones. Los materiales tienen múltiples aplicaciones, ¿verdad? Ahora vamos a hablar del trabajo en específico, ¿verdad? ¿Cómo estamos creciendo estos materiales? Estos los estamos creciendo por el método de RF sputtering. Entonces, donde agarramos unos targets que son unos discos del sulfuro de zinc, ¿verdad? Y estos se bombardean, ¿verdad? Por medio de iones de argón. Y los átomos del sulfuro de zinc salen, ¿verdad? Salen, digamos, evaporados y se pueden pegar a un sustrato. Entonces, por eso podemos hacer una película delgada del material. ¿Por qué hacemos películas delgadas? Porque muchas de las aplicaciones solo necesitas una cantidad de material infinitesimal del orden de metros, o sea, de 10 a la menos 6 metros. No necesitas más material. Entonces, los costos, el costo último de un dispositivo, ¿cuál es? El costo de los materiales en los que está hecho. No puedes bajar más allá de vos. Entonces, cuando tú utilizas menos material, vas a tener un dispositivo que puede ser usado por más personas porque su costo es menor. De allá vienen las celdas solares, por ejemplo, de tercera generación de película delgada. Solo es un cachito de material que usamos. De allá vienen los catalizadores, porque es solo la superficie la que se usa. Se crece con argón. Le pusimos una temperatura de sustrato de 150 grados centígrados, una potencia de 100 watts y una distancia como de 8 centímetros, ¿verdad? Donde hay el plasma de argón que se forma y el sustrato, ¿verdad? Y luego esas muestras se analizan de una manera relativamente estándar, ¿verdad? Que es con microscopía electrónica para saber, primero, cómo creces el material y después tienes que ver cómo obtuviste realmente. No es tan directa la relación. O sea, sintetizas, creas y después mides el producto, ¿verdad? Se usa un microscopio electrónico que tiene un dispositivo para poder cuantificar, ¿verdad?, cuántas impurezas tiene el material. Es un dispositivo que trabaja con un cañón de electrones y de allá salen rayos X y esos rayos X pueden decir qué átomos hay en el material. Luego tenemos la caracterización estructural por difracción de rayos X. La difracción de rayos X nos dijo cómo son los materiales. Y ahora usamos la difracción de rayos X para saber cómo son los materiales. Pero ahora hay algo muy interesante en esto. Nuestro concepto de material cristalino vino por los experimentos de difracción de rayos X de principios del siglo pasado, en donde los materiales son perfectamente cristalinos, tienen un arreglo perfectamente ordenado, y eso nos da lugar a picos en el patrón de difracción. Al observar los picos del patrón de difracción, tú dices, este material, ¿verdad?, y lo puedes complicar con teoría de grupos para hacer un análisis muy profundo. Este material es cristalino. ¿Sí? Aquí lo que vamos a ver es la otra parte. ¿Okay? Pero el material es cristalino y tiene esa estructura PCC, PCC, hexagonal, tetragonal, etcétera, todas las que se conocen. Entonces, con estos experimentos de difracción, podemos saber la estructura de largo alcance. ¿Cómo es este material? Cuando tú lo ves a lo lejos, con los miles o millones de átomos, 10 a la 23 átomos, mucho más que millones, 10 a la 23. Luego, bueno, se le miden algunas propiedades ópticas, ¿verdad? Para ver cómo reacciona con la luz, ¿no? Y lo que hicimos también es hacerle absorción de rayos X. Esta absorción de rayos X es una técnica que te mide la estructura atómica, pero ya no te la mide desde lo lejos, viendo todo el panorama macro, sino te lo ves. Puedes medir distancias interatómicas. ¿Okay? Entonces ya te vas a lo más microscópico y ves cuáles son las distancias interatómicas que hay entre los distintos elementos, ¿no? Aquí, bueno, algunas fotos, ¿verdad? De algunas muestras. Por ejemplo, aquí está con cobalto, con níquel y con vanadio. Son esos tres elementos que estuvimos trabajando. Las muestras crecieron con vacancias de azufre, como podemos ver en la relación zinc-azufre. Esto es muy típico en el sulfuro de zinc, que crezca con vacancias de azufre, ¿no? Aquí también tenemos algunas vacancias de azufre. Y aquí tenemos la composición en cobalto, en níquel. Son cantidades muy altas. Y aquí cantidades extremas. Pero vamos a ver lo interesante que esto resulta a la hora de hacer el análisis estructural. En este caso, por ejemplo, tenemos el mapeo de elementos, ¿verdad? Nos da por colores los elementos que tenemos, que son pues azufre, zinc, y aquí en este caso el níquel. Esto nos sirve para ver si tenemos segregación de algún elemento. Se hace un mapeo. Pues aquí tenemos, ¿verdad? La difracción de rayos X. ¿Y qué es lo que estamos viendo? Vean esto, qué interesante está, ¿verdad? Bueno, le dice, ¿no? Esta es la muestra con 0% de cobalto, con el 3%, y esta es una barbaridad, 14%. Nosotros estamos estudiando estos materiales en prácticamente aleaciones. Ahora, aquí abajo, no hay ningún pico, y esto es lo importante, que me muestre la presencia del metal, que me muestre la presencia de cobalto metálico. Aquí no hay ningún pico que me muestre la presencia de níquel metálico. ¿Okay? En este no podemos decir mucho, ¿verdad? En el vanadio, por el vanadio es un elemento muy interesante. ¿Qué hacemos con esto? Le tomamos el parámetro de red, ¿verdad? Y vemos que hay una contracción en la estructura. ¿Qué es una contracción en la estructura? Tú pensarás, ¿verdad? Lo que se piensa tradicionalmente es que todo el material se hace más corto, porque disminuimos el parámetro de red. Pero un análisis mucho más profundo nos va a mostrar que eso no es correcto. Que lo que está sucediendo es que cuando entra la impureza, la distancia a sus primeros vecinos es más corta. Pero todo lo demás del material se queda igual. O sea, las distancias interatómicas se conservan en los materiales. Aquí vemos el mismo fenómeno, ¿verdad? Entonces, eso es algo que estamos viendo. Mete la impureza, el parámetro de red se hace más pequeño. Esto es algo que han visto en la ley de Vegar, ¿okay? Que cuando se meten impurezas cambia el parámetro de red. Nada más hay que tomar en cuenta que no es en todo el material. Transmitancia y band gap. Bueno, una de las cosas que estábamos viendo es, está tremendamente interesante, que es la motivación. ¿Por qué le quieres poner tantas impurezas a un material? ¿Qué es lo que quieres lograr? Esa sería la gran pregunta. ¿Qué es lo que quieres lograr? ¿Qué estás buscando? Entonces, los materiales tienen la banda de valencia y la banda de conducción. Y cuando metes impurezas, esas impurezas se pueden ir por ahí del centro de la banda. Entonces, si se van en el centro de la banda, entonces puedes tener un material que tenga un gap, ¿cómo le llaman? Es una banda intermedia, una banda intermedia, ¿no? Entre estas dos, y entonces puedes tener un material que sea muy eficiente, porque aquí te agarras de energías altas, y de aquí a aquí, de aquí a aquí, te agarras de energías intermedias, entonces puedes mejorar mucho la eficiencia. Eso, miren aquí qué interesante está aquí con el cobalto, ¿no? Que tenemos esta transición y tenemos esta transición, ¿no? Entonces, aquí lo más interesante es que estas son transiciones DD, ¿no? Y es de la transición SP normal. En estos otros no nos ocurre lo mismo, ¿verdad? Aquí tenemos ¿cómo se llama? El gap, la medición del gap de cada uno de ellos. Entonces, esto es cómo se comportan estos materiales en general y una comparativa entre ellos. Ahora vamos a ver el caso estructural, que es el que nos compete aquí. La estructura fina de absorción de rayos X. Esto, lo que estamos viendo acá, estos picos, ¿verdad? Aquí está en el zinc, ¿verdad? Azufre y cobalto. Esto que estamos viendo es que vienen los rayos X y cuando los rayos X le pegan a la energía del electrón 1s, ese electrón 1s sale disparado, sale de la... ¿Okay? A las energías bajas, a estas energías, lo que está probando esto es los estados desocupados en la estructura electrónica del material. Entonces, en esta región de hexanes, de 6, probamos la estructura electrónica del material. No de estados ocupados, de estados desocupados. De aquí podemos ver cómo se comportan algunos de ellos, ¿verdad? Que hay una disminución ligera en esto, en este umbral. ¿Qué significaría una disminución ligera en el umbral? Que los estados desocupados se están ocupando, ¿no? Vemos esto aquí también. Se observa una aparición de preumbrales del KH del azufre, ¿verdad? Y esto se relaciona con algunas transiciones y estados de hibridación desocupados, ¿no? De S3B a cobalto 3B. Fíjense en este asunto. Luego de todo esto, se hicieron simulaciones también para poder entender qué es lo que está pasando ahora. Entonces, estas simulaciones se hacen con métodos ab initio. El programa PEP, es este se hizo con el PEP 10, ¿verdad? Y se simulan diferentes efectos, ¿verdad? Las vacancias, sobre vacancias de zinc, vacancias de azufre, sustitución de cobalto, contribuciones y cuál es el conjunto de defectos más probable que hay en el material, ¿no? En este caso, ¿verdad? Lo que estamos viendo, vamos a ver, ¿verdad? Es cómo se está comportando la estructura electrónica del material. Pero aquí nos vamos a que cuando tú rebasas ese umbral de absorción y vas a energías más altas, el fotoelectrón que fue inyectado por el rayo X que vino, se inyecta el fotoelectrón y ese fotoelectrón colisiona con los átomos vecinos. Al colisionar con los átomos vecinos se forman interferencias, porque el electrón es una partícula, ¿verdad? Pero que se puede comportar como onda. Entonces, al comportarse como onda, hay interferencia constructiva y destructiva al eyectarse del átomo absorbente. Y estas oscilaciones son las interferencias constructivas y destructivas que observamos. Estas interferencias se les puede hacer una transformada de Fourier y obtenemos una función radial de distribución. Esta función radial nos dice las distancias interatómicas. Pues ya no dependemos de la difracción de rayos X para ver la estructura cristalina del material. Esto solo es la distancia entre el átomo absorbente y su vecino. Vamos midiendo esa distancia. Y entonces se hacen todos los ajustes, ¿verdad?, que hay que hacer en la estructura atómica local. En este caso, ¿verdad?, no detectamos, aunque hay grandes cantidades de cobalto en el material, no hay segregación del cobalto. Cuando ustedes tienen un material como este, tú le agregas una impureza, ¿verdad? La energía va subiendo y se va a estabilizar segregando el material. Aquí no hay ninguna segregación en este cobalto y por eso resulta sumamente interesante. Y podemos medir la contracción que hay alrededor de las impurezas, ¿no? Aquí podemos reportar las distancias y cómo van cambiando, ¿verdad? Cuando se incorpora el cobalto en sustitución del zinc en la red cristalina, ¿verdad? El dopante agrega una segunda banda de absorción que se conecta a transiciones DD. La disminución de la línea blanca nos indican estados alrededor del átomo absorbente se están ocupando, ¿verdad? Los PRIESH, tanto de los hexane del azufre como del cobalto, nos indican que el cobalto se enlaza con el azufre, generando las transiciones azufre-cobalto. Esto se vuelve evidente en el edge del azufre. Revelan los EXAFs el carácter sustitucional del cobalto. El cobalto está entrando en la red sustitucionalmente. Nos revelan el tipo de defecto que hay en las muestras, que es la vacancia de azufre. Si nos vamos al caso del níquel, ¿qué es lo que sucede? Tenemos una disminución en la línea blanca, tenemos que aquí están los X6, voy a apurar un poco, ¿verdad? Tenemos aquí la estructura de absorción de los rayos X y las transformadas de Fourier. Y entonces vemos algunos cambios importantes. Vean esto. Aquí están todos muy parecidos. Nada más tenemos un pequeño cambio por efecto de distorsión. Pero aquí ya tenemos un cambio importante, ¿no? Si hacemos un ajuste en la estructura, nosotros podemos ver cuáles son los vecinos de cada uno de los átomos. Y en estos vecinos encontramos evidencia de nanocúmulos metálicos en el material. Quiere decir que en el caso del níquel, cuando rebasamos el límite de solubilidad, que se llama, se empiezan a generar nanocúmulos del material, normalmente en las interfaces entre granulos. Ahora, esto es importante por una razón. Difracción de rayos X no nos dice que eso es ocurriendo. Solo una técnica de esta naturaleza nos puede decir en qué momento empieza a funcionar. Cuando difracción vea esto, es porque ya hay un montón. Porque ya tienes un material en punto muy grande. Entonces, esto podría tener aplicaciones sumamente interesantes en la catálisis, donde tienes cúmulos de material, donde tienes nanocúmulos de metales. ¿Verdad? Finalmente, podemos ver el sulfuro de zinc con vanadio. El vanadio, ¿verdad? Se le hizo análisis de XPS porque entró con múltiples valencias. Esas múltiples valencias se pueden observar haciendo una correlación con otros estándares del material. ¿Ok? Entonces, ¿qué es lo que sucedió con el vanadio? Entró con 3 estados de oxidación en el mismo material. Entonces, el material, conforme le vas poniendo cada vez más vanadio, el vanadio se va acomodando para minimizar la energía total del sistema. ¿Cómo? Cambiando sus números de oxidación. Entonces, conclusión general, el cobalto tiene una mayor solubilidad en la matriz del sulfuro de zinc, pues incluso a altas concentraciones mantuvo su carácter sustitucional. En todas las muestras se pudo observar el carácter sustitucional y siempre se observó una disminución en la distancia de menos especial, un corrimiento, ¿no? Creo que estamos a tiempo, ¿no? Muchas gracias.
¿Alguien tiene alguna pregunta? ¿Sí?
Allá atrás.
¿Pueden pararse y hacerle en voz alta, por favor?
Pues yo creo que tiene una aplicabilidad, o sea, la combinación del grafeno con este tipo de materiales es muy útil, porque normalmente este tipo de materiales se van compensando y conductividades limitadas. El grafeno con su alta conductividad puede lograr introducir cargas al material, ¿no? A las cargas del material. Entonces, la combinación de los dos materiales es muy lógica para aplicación. No sé si eso por ejemplo no pregunta. Esto nos puede dar la área cotidiana, por ejemplo, por esto para controlar la actividad, sí, totalmente. Bueno, ¿en qué casos, no? ¿En qué casos? Hay una cuestión, podemos hacer una división un poquito artificial, no es una división entre lo que es el conocimiento básico y lo que es las aplicaciones. Entonces, en este caso, estamos poniendo conocimiento, ¿verdad?, básico sobre el comportamiento del material y cómo reacciona a los distintos metales de transición. Ahora, evidentemente, esto nos puede dar lugar a aplicaciones porque tenemos el material que tiene un ancho de banda muy grande, que se ubica a energías muy interesantes. Entonces, tanto la banda de producción como la banda de valencia están en energías muy interesantes, pero a la vez no, al tener ese ancho de banda tan grande, no lo podemos utilizar con la energía solar, o no lo podemos usar eficientemente. Entonces, al tratar de hacer la banda intermedia, ya aumentaría su eficiencia solar. Ese sería el punto, ¿no? Y luego, por otro lado, experimentar nanocúmulos de materiales que son cúmulos muy pequeños, que nos pueden tener propiedades muy interesantes, que son las cosas que vamos a estudiar ahora. Es lo que sigue.
Ok, una última pregunta.
Acerca de la aplicación de los rayos X, elementos que dependiendo de la configuración electrónica del elemento, conforme el rayo X, los rayos X te dan la información de que están ocupando valentes dentro de.
Sí, tú tienes un átomo, ¿no? Y ese átomo tiene el shell K, de los electrones 1s, es una esferita. Luego tienes el siguiente cascarón, que son los electrones 2s, 2p. Y luego tienes otro cascarón formando con una cebolla, los 3s. Cuando los materiales se enlazan, ¿verdad?, es la última capa la que se ve afectada. Entonces, al verse afectada esa última capa, se generan estados extendidos en el material. Entonces, se generan estados continuos, que es lo que hace la Basic Functional Theory y todas esas cosas que analizan todos esos estados. Entonces, ¿aquí qué hacemos? En el estado 1, en el shell K, en el más interior del átomo, ese no se ve afectado por la interacción química, por el enlace químico. Ese se queda a la energía donde siempre ha estado, ya sea que tengas el átomo aislado o ligado a otro. Entonces nosotros agarramos, tiras un rayo X con la energía que necesita ese electrón para salir del material. Entonces, Cuando tú tienes este proceso que hay un rayo X de entrada, un electrón 1s, entonces lo que tienes tienes que hacer la probabilidad de que el evento de pasar el electrón de 1s al estado continuo suceda a través de un campo electromagnético, se llama una transición dipolar. Entonces, viene el rayo X, saca el electrón, pero el electrón tiene que tener a dónde llegar. Si no tiene a dónde llegar el electrón, no va a ser eyectado. Entonces, el electrón solo va a ser eyectado del 1s, cuando tenga un espacio para llegar. Entonces, si estamos en esta fila, él es el electrón 1s, ¡pum!, sin energía del rayo X, es solo para llegar hasta aquí. Él no la agarra, simplemente el rayo X pasa. Pero sin energía suficiente para llegar hasta aquí, entonces él sí sale. Entonces, por eso decimos que probamos los estados desocupados. Entonces, si no, no puede salir. O sea, el material se vuelve transparente a los rayos X. El material va a dejar de ser transparente cuando haya un estado desocupado del otro lado. Le pegamos, por ejemplo, el hidrógeno. ¿A qué energía está su electrón 1s? 13.8 electrón volts. Si no le pegas a eso, no sale el electrón. Aquí estamos hablando de como 12.000, 13.000, 15.000 electron volts, ¿no? Entonces, cuando tú le pegas esa energía y él tiene a dónde ir, sale. Y si tú te pasas de esa energía, entonces va a agarrar y rebota por todos lados. Y ese rebote lo analizamos estructuralmente.
Ok, le vamos a dar un aplauso al doctor.
Jóvenes, nos vamos a dejar con una película.